Hello everyone. So I'm here to explain about, I'll introduce myself first. I'm Yathin from India. So I'm here working as an research intern at DSF. So here I am to talk about the topic enhancing security and usability of cryptocurrency wallets. So we are probably using crypto wallets as we are researchers and from the industry. We always use crypto wallets and we analyze about finance, right? But it's like we manage our cryptocurrency totally on our crypto wallets or exchanges for trading. So there's a myth. It's I just read out. This is the ChatGPT version of what is a cryptocurrency wallet. It is a digital tool that allows individuals to securely store, manage, and interact with cryptocurrencies. It serves as a virtual wallet for holding digital assets. It's a myth. There's a flaw in this definition, right? It doesn't store our cryptocurrency and it doesn't hold our digital assets. All it does is it just manages the cryptocurrency. It manages the private keys. We have many wallets such as Blade Wallet, which is developed which is from the Hedera, and it holds the H bar. And we got Binance, Trust Wallet, Electrum. We got many wallets, so it's up to us which one to use. So for our motivation, it's we were analyzing the attacks that were made in the past. It was worth around 16.7 billion since 2011. So that's huge amount to be stolen. So these were the attacks we have researching, and then we have found out. So this was our little motivation for our project. So we have we'll be using the wallets on regular purposes and daily activities, but we have not seen the background of wallets, what exactly happens when we create the wallet or when we enter the 12-phase mnemonics. So it's the symmetric key. These are the basic stuff. There are private, there's no private key and public key here. It's only single key where you can encrypt with encrypt the plain text, and then it converts into the ciphertext, and then you just put back the key, the same key, and it again converts back to the same text. This is called a symmetric key. And then asymmetric key, where we got private key and public key, so we can encrypt. This is you just encrypt with the public key first, and then you get the ciphertext, and you have a private key where you can decrypt using the private key. So you got two keys here. And then we have hashing, where you got a hash function where you just put the whole text into the hash function and it gives you an output. It's fixed size for different hash functions. And this is finally the digital signature, where there is a signing process and verification process. So initially we use contracts, right? We just sign on our contracts saying that this is me. So in blockchain, we doesn't have the signing capacity to sign by pen or pencil, so we just use our keys to sign. So what we do is we can sign any text or anything on the blockchain or a transaction on blockchain, and then we can verify it using our keys. So how do we use the whole cryptography in wallets? So this is MetaMask. So we got 12-phrase mnemonics, and we just get this. We just put it in, and we just enter the password, and then we get the whole wallet, the private key and public key. But we have why we're using the whole cryptography behind this. It doesn't make sense for a normal user. If I'm not into the cryptography or I don't want to understand the security, then it's not to be too useful. But if I'm using the wallet, I have to understand the security behind it, what exactly its driving force. So this is the 5-step process to create a wallet. You can create it on your own. You just need to randomly enter 128 bits of entropy, random 1 and zeros, and then after entering the 128, you just need to have a checksum. So it's entropy length, that's the 128 by 32. So it comes out to be 4. So we just append the 4, that is 0, 1, 0, at the end. So we basically do the checksum here, and then we get the whole numbers for each and everything. So we divide it based on sets, and we get the particular number for each and every set. And then we convert this into the word list. So we have a word list. So we just find out like the number like tagging to the word, and then we just put all the words, and this is the 12-phrase mnemonics which we use on our wallets. So we use the mnemonic sentence and the passphrase if required, that's not necessarily required, and this we put into a function called as hmac. So this function will generate the seed. This seed isn't our private key. This is just a seed that would be useful to create the private key. So we have the seed which is generated previously, and then we have the hmac, and also we have the Bitcoin seed for Bitcoin addresses, and as well we have a process for this, like the whole thing gets into the hmac 512, and then we create 512-bit hash using hash function, and then we just divide the hash into two parts, that is left and right, or first 256 and the last 256, and then we have the master private key. So this master private key, we can use it to derive the public key, and then the last 256 bits is used as the chain code. So this can be used to generate many addresses from the same. So then we can check on our taxonomy. So these are the different types of wallets that are into existence. So first we divided it into based on funds controllability, that is custodial and non-custodial, and then internet connectivity, that is hot and cold. So there have been overlaps to enhance the security. So it's like we have cold custodial wallets, cold non-custodial wallets, hot wallets that's into custodian and also non-custodian. Also we got hardware, software and paper wallets, which are like, it's three-dimensional, right? It's many. So we use the capacity of each technology, and we basically put everything into one to enhance the security features. And we got brain wallets at the other end, which is like which will help you to you not memorize these 12 keywords. You just need to memorize a password and then put the password into it and generate your wallet. So there's one more. There is another set of wallet called as semi-custodial wallet, which uses the capacity of a server as well as the human beings. It works this way. Say I'm the user, I just enter a username and password, which is like turns into the whole set of process and then generates the private key using a server. So say if you don't have any, if you don't have a capacity to remember all the 12 set of words, it should be easy, right? There must be some process to evaluate things and then come out with an outcome where you just need to input the username and password, and then you can generate your private key. So I'll just explain this simply using an animation. So you can say that is me, and then you just enter your username and password, and then you just use a hash function to hash it, and then you get the hash username and password, right? And then you keep the password aside, and then use a point on elliptic curve, generate a point on elliptic curve using the username, and then you get the point P. Also we generate a random value called as CR for the client side purposes, and then we basically we use exponentiation function, elliptic curve basically. So we use point and random value to exponent it, and then we generate alpha. This alpha would be, we'll be using post request to send this alpha to the server. On the server side, we have alpha and as well as random value, that is server side generated, and then we again use the exponentiation function to generate the beta. So this beta would be sent to the user as a response to the post request, and we have, so these are the current things I'm having: beta, random value as well as the hash password, right? So what I do is, first I will try to create the inverse of this random value, because it's like, say we need inverse of 2. So for multiplication it's 1 by 2, and if it's addition it's minus 2, right? So similarly we'll be creating an inverse for this. So after creating the inverse, we get the inverse ICR, and then we use exponentiation for beta and inverse, and then we get gamma. So we use gamma and hash password, and we use Shamir's secret sharing scheme, where we get the where these two would be the input, like it's 2, 3 Shamir's secret sharing scheme, and we get the output as secret and the third share. So this third share, we can store it safely anywhere. Like you just need to use it like when the server is down. If the server is active, you can just you enter your username and password and you can generate this secret. So this secret is working like your private key. And this third share would be, securely at your vault somewhere, offline vault or anywhere. So whenever the server is down, only then you'll be using this third share to generate your private key. So in our research, we were we were discussing on possible set of attacks. So these were the different attacks that were possible. On the network side, we have routing, de-anonymization, man in the middle, domain name system, denial of service. And on the application side, we have social engineering, routing and debugging, faulty libraries, malware, storage, and these are the programming vulnerabilities for smart contract wallets, and as well, this is for the authentication. So, coming to the routing, it's like we just cluster the blockchains, and then whatever transaction comes into account, we just route it, or we can just divert it. So we can just stop the transactions. And de-anonymization is like the word itself says, we are just de-anonymizing a user, like we are just trying to find out who that person is using the IP address tracing, and we got like the graph analysis of transactions. And man in the middle works similar to the routing, but it's quite different. It's like it works on the network layer. So whenever we try to push a transaction, it's like we change the addresses, or the we try to corrupt the transaction and then send it to the blockchain. And we got domain name system, where there are 3 types of DNS attacks, such as DNS cache attacks and DNS tunneling. And so these DNS attacks are like works on the DNS layer, where we try to send the user to the malicious applications. So it's like I just try to access a DNS, so the DNS will try to send me to the other server, which is malicious. And denial of service is like we just send many, keeps on keeping the server engaged into some other, we just send packets to the server and then it's too busy so that I can't access the server. And then we got social engineering. This set of applications work on our mobile phones. Say I have a mobile wallet which can be rooted, or it has faulty libraries, or it got malware, or there's some defects in the storage, like it's not encrypted, my private key is like open. And smart contract vulnerabilities like reintendency attack. So these attacks could be could store. The attacker can steal many cryptocurrencies or whatever if there's a flaw in the contract. So side channel, brute force, and dictionary are the hardest attacks. Like these are not too easy, but if there's a quantum computer, this would be like very easy. Like it can just snap the things up and it can create the attack very easily. So side channel attack works this way. Say I have my hardware wallet, so that generates the private key. Say I take the graph analysis of its power consumption while it's creating the private key, and then I just turns out to be like, say there's 1 and zeros, right? So if 1 is like the highest peak, 0 is the lowest peak of current, the power. So during that, I can analyze that 1 is the highest peak and 0 is the lowest peak, and then generate the private key back to its form. And brute force is like trying all the possible attacks on the wallet. So it's like our private keys are mostly encrypted in our mobile wallet, so we just try to decrypt it using all the possible combinations. And dictionary attacks works this way. In our mobile phones, we always use the keyboard, right? And we have our dictionary. So whenever we have the set of words, we just try to analyze the pattern, and then we can brute force the dictionary in our mobile phones and then create private key back. So these set of wallets are like, these set of attacks are like too heavy for the users, but mostly the attacks are taken care of by the wallet owners. So this is the diagram. Like we have got DDoS attack on the, it uses the botnet to create the attack on the server as well as the wallet software. And then we got brute force attacker trying to decrypt the private key which is stored. And we got phishing attack, which is like tricking the user into revealing the private keys. And then we got man in the middle attack, which is like there's a malicious connection between the sender and the blockchain to create the just routing out the transaction. So you can go through this slide. And then we also got defense mechanisms. These are the possible defense mechanisms that are like implemented. So on the network layer, we got RPC with TLS. So it's like a remote procedure call with the transport layer security, where everything is encrypted while sending it to the blockchain, and then it's again decrypted on the blockchain. And then we got architectural shift to the IPC. So IPC works this way. IPC is like inter-process communication, where the communication between a process and process within a software or within a device is called as IPC. So they want the research wanted to suggest that they want to shift from RPC to IPC, which is more secure. And then the stealthy approach, which is like you don't use your private key or your public key to sign transactions. What you do is you generate a new public key and then you sign transactions. And then we got was B wallet and Samurai wallet, which uses routing techniques, which basically creates many dummy addresses, and then they just send it to the dummy addresses first to create, to just keep the user anonymous. And then we move on to the authentication. So we move on to the application. So on the application side, we got encryption, two-factor authentication, a threshold cryptography. Then we got real-time verification, where you can like verify it using your camera, using OpenCV and computer vision techniques. And then we got implementing sensitive use, which works this way. Many times there are a few wallets where you try to take screenshot, it doesn't allow you to. So this is called as implementing sensitive use. It doesn't allow you to see your screen. So it's like totally screenshot proof and video recording proof. And we got trusted execution environment we created trusted execution environment to generate private keys and signing transactions. And then we have multiple backup wallets where private key is like split, and then you can use the threshold cryptography to again bring back your whole private key. And then moving on to the authentication, we got complex passwords. We have to always use complex password. It's same as like Web 2 word. So we have to limit the login attempts. Say I'm trying to log in many times, like 4, 5, to just to get out of from brute force attacks. I have to just limit the login attempts, and then we have to use captchas to increase the time capacity, and then we have to enhance the master seed as we have seen previously, making it much more random or using true random number generator. And then we have decentralized recovery by Dr. Lehman from the Hedera. So this works this way. Say I forgot my password, right? Or I lost my private key. I need my friends. So my friends or the helpers will help me to generate the private key back. Then we got smart contract, defenses where we can try. Basically everything's like too much fancy, but it's like mostly safe. It's just improve your smart contract, just try to make it optimized and secure. It's like, you have to just remove the mutex logs, and you have to enhance it using, safer arithmetic operations and exception handling. And then we got access control. Access control is mostly the, attacker's view, like they just try to access a function which shouldn't be accessed by them. So by conclusion, we got the brain wallets offer high security and usability. It's like easy to remember. And then we got paper and hardware wallets, which strike a balance between usability and security, but it's like hard for users to carry the hardware wallet everywhere we go. And then we got smart contracts are very easy to use, and it's very much cool to use because we don't need to carry anything. We just got the smart contract anywhere we go. but it's like the programming capacity of the smart contract depends heavily on the security. As well as the software wallets are most commonly used, as we all use now smartphones and desktop wallets. We just try to log in through web and then we get the wallet, right? And semi-custodial wallets are the new trend, and which is like which go hand in hand with the smart contract wallets. It doesn't need to, it doesn't need to create any or remember the 12 words, and you can just go, and you can also have the ability to rekey your private keys. So rekeying private key means you use the same set of username and password, but the private key changes. So that's something with these semi-custodial wallets. I like to conclude my presentation and would like to take up the queries.